Yeah, let us start here. So on the other day, we have started with image restoration, and there we have discussed about the degradation model and some algebraic approach for restoration, like averaging, median, mean methods. And now this class we are going to see the rest of the concepts, that is inverse filtering, least mean square filters, LMS filter, constrained least square restoration, and interactive restoration. So it is it is not interactive, in fact it is iterative. There is a simple mistake here in the printing. It is not interactive, it is iterative restoration. This iterative restoration is a nonlinear process. The rest of the methods, inverse filtering, LMS filter, constrained least squares restoration filter, these are all linear filters. Iterative restoration is non-linear filter, right? So here, for all this, we can develop in the MATLAB if you have patience, right? So let us start here from the last class. So in the last class, we have stopped here at the autostatics filter. So let me revise just for 2 minutes, right? So here we have seen in the last class different types of noise, right? So there in the last class we have seen what is degradation model and how do you represent the degradation function, or how do you represent the degraded image by using the degradation function. And if you apply the restoration process to that degradation function, you'll be getting the estimation of original image. That is what we represent as f cap of x comma y, and n of x, eta of x comma y, or capital N of u comma v represents the noise component and its Fourier transform respectively, right? So here in the last class we have seen different noise models and also their PDFs, density function representations we have seen, and also in the last class we have seen what is periodic noise, and in the last class we have seen estimation of noise parameters, and later for the restoration we have started the procedure, and that is algebraic approach, and there we have seen mean filters, order statics filters, and in the mean filters we have taken arithmetic mean, geometric mean, and harmonic mean filter, contra harmonic mean filter. So these are the things already discussed in the last class, right? No need to worry here. And coming to order statics filters, in the last class we have discussed about median, max min filter, midpoint filter, alpha trimmed mean filter, right? So in the median filter we are going to arrange the pixel values and we are going to find the median. Similarly, by arranging the pixel values, we are going to find out the maximum and minimum values for the max min filter. For the midpoint, by taking the max and min values, we take the average of it for the midpoint. In the alpha trimmed, we are going to remove some components from the selected, or SXY we usually call, that is the selected region of pixels, and from that we are going to trim a set of pixels. After trimming we are going to find the average or mean, that is nothing but our order statics filters and adaptive filters. So in fact you don't have this in your curriculum, but for your understanding I am giving some discussion on adaptive filters. So basically here the adaptive filters adapted to the behavior based on the statistical characteristics of the image inside the region. So the SXY is nothing but the region which we are selecting for the operation. That is called filter region SXY, and there we represent statistical characteristics. And here we have two types of processes, image processes, or two types of restoration. One is deterministic, other one is statistic. That is deterministic procedures we have and statistical procedures we have. And here one of statistical procedure is using adaptive filters. Here it is adapted to the behavior based on the statistical characteristics of the image inside the filter region. And it is improved versus, and anyway, I'm not going to discuss much about this adaptive filters. That is not there in your curriculum. And here, one of the example for the adaptive filter is adaptive local noise reduction filter. And here, why I'm concentrating on adaptive local noise reduction filter is here, you know, something about this particular terminology of this particular filter. And the only thing is we need to know the mean and variance values of the particular region which we have selected. That is, as we are selecting or considering the statistical characteristics, we are going to take the mean and variance values, right? And also we need to know the parameters like in the local region only. Parameters like g of x comma y, that g of x comma y, which is already mentioned in the last class, that is noisy image pixel value is called g of x comma y. And the other one is noise variance. We represent with sigma square, right? And the mean value, local mean value, that is ML. And local variance, we call it as sigma L square. So these are the parameters must be known to apply the filtering process here, right? And here analysis, what we are going to do is, if at all if the noise variance is 0, it returns complete g of x comma y. If at all if the local variance is greater than the noise variance, and it returns a value close to g of x comma y. If at all if local variance and noise variance both are equal, it returns the mean value. And there is an algorithm that we use for implementation of this adaptive local noise reduction filter, right? So the only parameters we need to know are the variance of the noise and the local variance and local mean. Based on these values, you are going to get the estimation, right? And the estimation you can represent like this: the estimation of the f of x comma y after the restoration or the restored image can be represented as, that is the degraded image minus the variance of noise by variance of local variance of SXY, that is the selected region, into g of x comma y minus ML. It is a filter operation. That is the result of the filter operation, that is adaptive local noise reduction filter, right? So it is one of the example for adaptive filters. So as we have discussed mean filters, that is where you are going to find the average or mean value for finding the estimation. Similarly, in order statics filters, we are going to use median or maximum or minimum, or other one is alpha trim mean filter. So like that, we have this particular adaptive filter, and in this adaptive filter, we are going to find the estimate by using this particular relation, right? And next, periodic noise can also be reduced. So another parameter that we have discussed in the last class is another noise model is periodic noise. So as I said, periodic noise is nothing but a sinusoidal noise. And ultimately, we are all aware of it, the sinusoidal noise, in the sense, if I take the Fourier transform of the particular sinusoidal noise, you know that we'll be getting a pair of impulses. Pair of impulses. Why? Because the Fourier transform of the sinusoidal signal is pair of impulses, right? So here, if I take the Fourier transform of the particular image with the sinusoidal noise or periodic noise, you can find two impulses on its Fourier transform, right? So there, by applying, for example, by finding the Fourier transform of the image itself, you can find this particular periodic noise. That is, you can find the impulses in the Fourier transform of the image. By seeing the impulses, you can understand at what frequency we have the noise component. And therefore, by using various filters like band rejection filter or band pass filter or notch filters or optimum notch filters, and these are all discussed in the enhancement method, frequency enhancement methods in the second chapter. Already we have discussed frequency enhancement method in the enhancement in the frequency domain, and there we have discussed band rejection filter, band pass filter, notch filter, and optimum notch filter. All these things are discussed, and some Butterworth filters, Chebyshev filters, all the filters are discussed in this second chapter only. Therefore, I am not going to concentrate on this, right? So it is the complete structure of restoration models or restoration methods, and the restoration methods are, we have deterministic methods and we have stochastic methods based on the statistical nature of statistical parameters. In the deterministic methods, again we have linear methods and non-linear methods. And linear methods, again we have inverse filtering method, least mean square or minimum mean square. The other name for the filter here is LMS filter is least mean square or minimum mean square, and it can also be called as Wiener filter. The other one is constrained least square filter. Whereas in the non-linear methods, we have iterative restoration, right? So these are the methods we have for the restoration of the image, which is maybe degraded by, as that is by the time when we are capturing the image or when we are transmitting the image, right? So first one, so we have how many types? Linear and non-linear. So let us go with linear first. So in the linear, inverse filtering. So here, inverse filtering, the basic idea of the inverse filtering is removing both noise and blur. Where that is our target is here, noise as well as blur. Blur is due to the capturing device, whereas the noise is due to the channel while transmission, right? So the restoration result with inverse filter is basically that it is one of the drawbacks of inverse filtering, in fact. So here we can try for the removal of noise as well as blur, but ultimately by using inverse filtering, almost we can reach, but not it is perfect, right? Filter is not usually perfect, but its major advantage is it is a very simple to implement. So with the estimated degradation function, we are all aware of it. That is g of xy is a degraded function equal to f of x comma y into g of h of x comma y. It is the impulse response of the degradation plus noise component n of x comma y or eta of x comma y. It is its Fourier transform representation. And here onwards, here for simple understanding, I am just representing this like this: g equal to hf plus eta. That is, this particular thing is represented like this, right? Now inverse filtering, so that is g equal to hf plus n. So from the above equation, and we are going to find the error. That is, error is what? Nothing but noise. So here a noise equal to g minus hf. As I said, what is our target here? Reduction of blur as well as reduction of noise using inverse filtering. So that is, our target is to reduce the noise component eta or n, right? Eta or n. Here we wish to ignore eta and use f cap to let hf cap approximation it under the least square sense. Here, so usually here, as I am saying, least square sense. So you might have seen in the previous methods and some digital communication subject also. That is what we are targeting here, the noise component. and what we are targeting for to estimate the image, that is f of x, that f cap of x comma y, right? So here the error function I am taking least square function as g minus hf cap square. Why? Because here the error, in the sense error is calculated by using the estimation value and the estimation value. Is it right? So therefore here from this n equal to g minus hf is the noise component. So after the estimation here, the function will be f cap, will be with f cap. So that is g minus hf cap whole square is called square, least square error. That is error square. I'm considering this as a function j function. So they basically here what we wish to obtain here we wish to obtain minimum value for jf, and f cap is not constrained in any other way. Therefore, it can be termed as unconstrained restoration. See here, we are not putting any constraints here, and we are not putting any limits here, and therefore it is called unconstrained. So why I am concentrating on the word unconstrained or constrained, and soon you are going to see what is constrained filter also, right? So we are going to put some constraint, right? So here it is unconstrained restoration, and here therefore this particular equation can be represented as I'm taking the square here, and it is expanded. So what is the target here? To minimize this, and to find the minimum we have to minimize this such that the f cap will be the perfect estimate. That is the target here. How do you minimize this for finding the f cap? I repeat, by minimizing this error, least square error, we are targeting for the estimate, that is f cap. So what should be minimized here? J of f cap must be minimized. So for minimization, you know the basic procedure for the minimization, that is you have to find the differentiation of that particular function, and you have to make it equal to 0. You have to make it equal to 0. Then you can find this particular f cap, right? So that is we have to write the expression for j of f cap in terms of f cap by, that is error function. That error function must be minimized to find the f cap, that is estimation value or estimation function, and therefore here that particular differentiation value is calculated. Now if I solve the equation here, so how do you solve the equation? This particular function is equal to 0 for finding f cap. So after calculations, I can write the f cap as, so you can do simple calculation. It doesn't take much time, just 2 to 3 steps more required here. So what is f cap here? It is the estimation value of the image, or the restored image of f of original image f of x comma y. F of x comma y is original image. F cap is restored image. That restored image or estimated image can be represented like this by minimizing the error, that is j, right? So it can be taken as f cap equal to h inverse g. So here, therefore, what you can conclude is, if I take the Fourier transform here, h inverse g, if I take the Fourier transform of this particular spectrum of estimated image can be represented as g of k comma l by h of k comma l, and don't be confused with the k comma l values. That k comma l nothing but m comma n in the previous slide, right? So in some literature it is given as u comma v, and in some literature it is given as k comma l, and just I am following your prescribed textbook literature, right? So it is taken from your second prescribed textbook. U comma v is as per the first textbook, Gonzalez. It is by the Jay Kumar, second textbook, right? So it is f cap of k comma l equal to g of k comma l by h of k comma l. So that is from this equation only this is written. So this is what the required estimate by using inverse filtering. So this is done by using inverse filtering, right? So therefore, what you can conclude here, f cap of m comma n or f cap equal to inverse Fourier transform of this particular f cap of k comma l or g of k comma l by h of k comma l. So this is what the procedure we follow in the inverse filtering. So here finally what I can conclude is, in the inverse filtering, the main target is to minimize the error. That is, for finding the estimation, we need to minimize the error. How do you find the error? That error is nothing but which error? Least square error. That is j equal to, least square means j equal to, so what is the least square? G minus hf whole square, right? And what are the drawbacks for the inverse filtering here? The major drawback of inverse filtering is that it is not always possible to obtain an inverse. Why? Because here, what are you supposed to do here? We have to find the inverse of h, and then you have to multiply with g to get f cap. This is the final procedure or final equation that you can write for. That is the final equation that you can write for restoration by using inverse filtering, right? And now, what is the drawback here? We need to find the inverse of the degradation function, and always it may not be possible to write the inverse of this particular degradation function. That is one of the drawbacks in the inverse filtering. Another thing is, for an inverse to exist, the matrix should be non-singular. Ultimately, always the degradation function must be a non-singular. Then only you can find the inverse of it, H inverse. And at the same time, it will not perform well in the presence of noise. That is the major problem. If noise is present, more noise is present, that inverse filter will not work. So if the noise is present in the image, the inverse filter will tend to amplify the noise also, which is undesirable. Therefore, in the presence of noise, it is better to go for the Wiener filter. So usually here, the degradation process is maybe due to the degradation while the image is captured, and during the transmission time, noise added during the transmission time. So therefore here, by using the inverse filtering, only you can target mostly for degradation while taking the image, while capturing the image. And if the noise component is more, in fact noise component is available in the image, it is not advisable. For that, in the presence of noise, better to go for Wiener filter. That is the second one, Wiener filter. So here, how do you write the Wiener filter here? The objective of this particular Wiener filter is to find an estimate of the uncorrupted image f of x comma y. F cap of x comma y is estimation. F of x comma y is original image, such that the mean square error between them is minimized. So in the previous one, we have taken least square, but here we are taking mean square. So how do you write the mean square here? We are considering noise also. In the inverse filtering process, we are not considering noise. We are considering only degradation while the image is captured. If the noise is present, the inverse filtering process is not acceptable, advisable in fact, right? So therefore, we go for Wiener filtering. So as noise component is present, ultimately that noise component will have the statistical nature. And why? Because we represent them as a random variable, So therefore here we find the error by using the expectation of f minus f cap whole square. We all know that the mean square value of the random variable can be calculated by using the expectation, right? So that is, the mean square value is calculated E of f minus f cap whole square, and it is assumed that the noise and the image are uncorrelated. So here another assumption is the noise and image are uncorrelated. If they are correlated, ultimately that mean square error will be 0, right? So therefore here we have to assume that this particular image and the noise are uncorrelated. Ultimately here in the real time, always the image and noise cannot be correlated, and that one or the other has 0 mean, and that the gray levels in the estimate are a linear function of levels in the degraded image. I repeat here, first condition is the mean square value must be calculated by using the estimation, expectation, and the other one is the image as well as the noise should not be correlated, or they must be uncorrelated. And uncorrelated means one or other has 0 mean. And the other one is the gray levels in the estimate are a linear function of levels in the degraded image. And soon you're going to see it. What do you mean by that? And therefore here, yeah, sir, but the error happens due to the noise. Then what's the use of inverse filter? Yes, so that is why again I'm saying here two types of degradation, two ways of degradation. First one is while capturing. In the very first class of this particular restoration process we have discussed. So that is, maybe if the image is in motion, if you capture the moving object, you can find the blur in the image. That is called degradation. Degradation. It is not comes under noise. In fact, noise means when it is transmitted over a channel. That is, unwanted things added to it is called noise. Unwanted things added to the original image or the image to be transmitted is called noise. So here my target is removal of motion blur. Yes, yes, no, not during capturing, to remove the error, if at all, to remove the degradation, or to remove the blur if you have any blur during the capturing. I'll show an example given in the textbook, and actually I tried in the MATLAB, but it is taking time. If possible, I'll show the output of the image by taking the real-time image. By taking the real-time image, I am going to show how the inverse filter will act. And just I'll show one image here. Just I'll show here. 1 second. This. 'Wait for a while, just 1 minute. I'll show you. Average filtering. Average filtering. One second. I've kept somewhere here. I'm not finding it in the right time. Just 2 minutes. Hold. What do you mean by motion? Yeah, at the end of the session, I'll show what do you mean by blur. Right? No need to worry. It is taking time, and let us continue just here. I'll show what do you mean by blur. Right? So just remind me while closing the session. I'll show what do you mean by blur. So simple example is taken, that is a horse. When the horse is moving, when the horse is running, so if you capture the image, so ultimately the captured image will have the blur, right? So that example is explained there, and just I would like to show that image, and I'm going to show at the end of the session, and no need to worry here, right? So here, coming to the winner filtering, so what I can conclude is inverse filter is not applicable if the noise component is available in the image, and only it is used to remove the degradation while capturing the degradation by any factor while capturing the image, right? So therefore here we go for winner filtering for removal of noise and as well as the degradation due to the capturing process. And we need to find out the estimate. For finding the estimate, here we take this particular relation. It is a derived function in the winner filtering process, right? So here that f cap of u comma v equal to, that is h of u comma v sf. So that is sf and sn or s eta, and these two are nothing but power spectral densities. And just remember this particular relation, that is h of u comma v is the transfer function of the degradation function, or you can also call it as degradation function, and the complex conjugate of this is h star of u comma v, and it is the derived relation. And you can remember this, the final relation here, that particular final relation is here 1 by h of u comma v into h of u comma v whole square by h of u comma v square plus this particular ratio of the power spectral density of noise and this image, right? So here this is the relation. For example, if this particular constant is not there, ultimately again it becomes normal inverse filter. That is, if noise is not available and ultimately power spectral density is 0. If power spectral density is 0, this particular ratio becomes 0. If this ratio is becoming 0 and this factor becomes 1, ultimately it will be g of u comma v by h of u comma v, and that g of u comma v by h of u comma v is nothing but again similar to your inverse filtering. So that is, if no noise component is available, the winner filter also acts as inverse filter, right? So here g of u comma v is transform of the degraded image. The restored image in the spatial domain is given by IFT, inverse Fourier transform of the estimate, that is f cap of u comma v. That is, after f cap of u comma v is calculated, and by applying the inverse Fourier transform, you can find the estimate, that is small f cap. Our ultimate goal is small f cap of x comma y, right? So here, what is h of u comma v? Degradation function. H star of u comma v is complex conjugate, and you know how to find this h of u comma v whole square. And what is this estimate of u comma v? Power spectrum of noise, right? Or you can also represent by using its Fourier transform of noise, n of u comma v whole square, right? Sf of u comma v is square of this particular f of u comma v. It is power spectral density of undegraded image, that is f of x comma y, right? So there is a difficulty in the winner filtering. That is, what is the difficulty in the winner filtering? You need to find the power spectra of both noise as well as original image, undegraded image, right? So here these two must be known for applying this particular Wiener filter. Why? Because here we are using the statistical criteria. Based on the minimizing statistical criteria, the Wiener filter is designed, right? So therefore here the other method we have is constrained method. Other method we have is constrained method. Other method we have is constrained method. So what is the constraint method? It is a linear algebraic method. So here what we do is, here we apply some mathematical calculations. That is, we assume them as matrices and we take the matrix multiplication simply in this method, just matrix multiplication. So in the constraint method, ultimately here we are going to take some constraint, just some constraint. So here it is assumed that there is no knowledge of noise present. No knowledge. So whether the noise is present or noise is not present, not required. And it is assumed that there is no knowledge of noise is present. And we take that f cap of x comma y as estimate. F of x comma y is original image. And here the degradation function is h. And these are the assumptions we take first. And what is the procedure we follow in the constraint method is, the restoration must be constrained by the parameters of the problems at the hand. So here are what is the constraint method? So here in the constraint method, the restoration must be constrained by what? Parameters of the problems at the hand. What do you mean by that? Yes, the what is the desired one is here to find the minimum of the criterion function. So minimum of the criterion function of what? What do you mean by criterion function? The criterion function is nothing but that is square of the Laplacian. So what is the Laplacian here? Again, Laplacian will give what? Laplacian will give change in both the directions, right? So here we know gradient operator. The gradient operator and Laplacian operators will give the changes. Will give the change. So here ultimately by finding the changes, we need to minimize the changes here, irrespective of the noise, right? Whether it is present or not. So by finding the changes, we are going to minimize the changes. So here, how do you minimize? By taking a constraint. So what is the constraint here? By subject to the constraint, that is G minus HF cap. Just in the previous Wiener filtering, inverse filtering, we have seen G minus HF cap. That G minus HF cap is called error. That error square equal to eta square. What is that eta square again? That eta square is called, in fact not eta, it is n square. That n square is norm. What do you mean by norm? That is, norm can be calculated by using this relation, a simple matrix multiplication. Just I have said, it is a simple algebraic method, right? And we know that delta square is Laplacian, right? So finally, how do you calculate that estimation here? That estimation can be calculated by using the relation. The only thing you need to remember is this particular relation. F cap of u comma v equal to h star of u comma v by mod h of u comma v whole square plus gamma into p of u comma v whole square. And h star of u comma v is a known function. H of u comma v is a known function. What is gamma and what is p of u comma v, right? And g of u comma v is also known function. That is, the Fourier transform of degraded function is g of u comma v. And what is p of u comma v? Fourier transform of p of x comma y. What is p of x comma y? P of x comma y is nothing but Laplacian operator, and which you might have seen in the image enhancement. Laplacian operator p of x comma y, right? So it is a mask. Laplacian mask. You can also call it as Laplacian mask. And what is gamma here? Gamma is the parameters must be used or adjusted so that the constraint in the equation 2. What is equation 2? So that is equation 2 is g minus hf cap whole square, which is equal to norm, Euclidean norm. So based on that constraint, that lambda value must be, gamma value must be adjusted. So how do you, that is the procedure we follow here. That is the procedure we follow here in the constrained method, right? So here I repeat, So total 3 methods in the linear processing are discussed. Linear restoring filter. So one is inverse filtering, the second one is Wiener filter, and the third one is constraint filter, right? So in the inverse filtering, the inverse filtering is used when the noise is not present. When the noise is present, we go with Wiener filter or constraint filter, right? So in the inverse filtering, we take the f cap or the estimation value as simply g of k, g by h, g of k comma l by h of k comma l. So in the Wiener filtering, we calculate that power spectral densities, and by finding the power spectral density, we take the relation for f cap of u comma v like this, right? And in the constraint method, so here that particular estimation is in the constraint method, we calculate the Laplacian, we calculate the gamma based on the constraint. That constraint is g minus hf whole square equal to n square, right? So here these particular values are going to be calculated, and then by using them we are going to take this particular estimated value f cap of u comma v, right? So here another method is nonlinear degradation, nonlinear restoration method. So here in the nonlinear, we have seen that is iterative method. So here a linear image restoration algorithm is capable of producing result directly from the observed data, right? So linear processor. From the observed data, we are going to take the algorithm directly, but it requires some form of inverse operator to be applied. Whereas in the nonlinear process, what we are going to do, we are going to take iterative approach. That is, we are going to find estimate now. We are going to compare. Yes, it is not satisfactory. First you compare, going to compare, and then again you change. Iterative. That is, again you change, and again you compare, again you change. So that is, nonlinear technique uses an iterative approach to produce successive improvement to the restoration until a termination of condition is reached. That is the algorithm for it, right? So first reblur, then compare with what? Observed image. Again, if you get any error, and again update the estimate. So it is the chain process until you get the restored image, right? So the objective is basically to minimize the error, which can be done through gradient descent approach. So here we are finding that f naught cap, which is equal to beta h transpose g. So what is beta? The beta is 0 to lambda max based on lambda max. So lambda max is already this equation is in terms of h transpose h is derived in the inverse filtering. In the inverse filtering, we have seen the expression for f cap in terms of h transpose h. We have derived by by minimizing the error. That is, the j of f cap function is taken, and we have taken the differentiation of j of f cap, j of f cap, and after finding the differentiation, we are going to make it equal to 0 for finding the f cap value with minimum error by minimizing the error, right? So in that process, we have calculated f naught cap in terms of h transpose h, and this particular h transpose h is represented in the form of lambda. I mean, in terms of beta. Yeah, that's it. That beta is what? The beta value lies in between 0 to 2 by lambda max, where lambda max is eigenvalue. Why it is? Why? Because it is a matrix. From the matrix, we are taking the eigenvalue, right? So here, as I said, it is an iterative process. We are going to take f cap of k plus 1 by using this fk cap, and we are going to take the change. What is that pk? Pk is nothing but change here. And pk is equal to h transpose into g minus hfk. So it is the complete algorithm we use for developing the constraint method. And if you develop this particular algorithm, we can find this estimate using the nonlinear process. In both Wiener and the constraint, which is the best, right? So in Wiener and constraint, so based on the application, so here mostly used one is Wiener. Mostly is just Wiener. Laplacian filter. Are there any replace Laplace functions? No. Laplacian in the sense what? Laplacian, gradient, Laplacian. You might have studied in the EMTL. Gradient means change in one direction. Laplacian is the change in the two directions. Why? Because it is a two-dimensional image. We take the change in the two-dimensional. So Laplacian is nothing but a second order change. First order change is gradient. First gradient must be calculated in the two-dimensional. And the second one is second order change is Laplacian. That we'll discuss this particular thing in the image enhancement only. Laplacian part. What is gradient? What is Laplacian? And gradient is used for what? Laplacian is used for what? And the both gradient and Laplacian are used to find the change in the pixel values. To identify the changes in the image, whether any change is there or not, or that is sudden changes are there or not. If the image is smooth image, and if there is any sudden change, then you can say that as some degradation or noise, right? No, Laplace functions are not used here. So basically that advantages are also mentioned here. I'm going to share the slide. You can go through the advantages of this particular iterative algorithm, and it is copied directly from your textbook, in fact, right? You can go through it. So finally here, total linear and nonlinear methods. In the linear methods, the nonlinear methods, it is complete iterative procedure. Iterative, that is, first you calculate, you compare. Now if not satisfied, then go back and again develop the estimate. If not satisfied, and again go back until you are reaching this particular final estimate. The procedure must be continued. Yes. So here with this we can conclude all the restoration methods. So all the restoration methods, right? So sample questions taken from the previous question papers, and some of the questions will be like this: explain the following order statistics filters: maximum filters, median filter, alpha trimmed mean filters. All already discussed about this. Enumerate the difference between image enhancement and image restoration. That part already discussed in the very first slide. And one is subjective, other one is objective, right? And explain about algebraic approach of the image restoration. Explain the principles of least mean square filter, LMS filter or Wiener filter, and obtain expression for filtered function. Already discussed filtered function f cap of u comma v, right? So like this, you can expect the questions. And still, if you have any doubt, and here actually the other day I said yeah. So Chaturya, for you here, your question. So here, what do you mean by without noise? You said inverse filter is used for what, sir? If there is no noise, and ultimately, as I said, while capturing, if there is any blur, to restore that image, we use this. So it is called blur, motion blur. And virtually, you can generate this particular image. For example, if you have this image, I would like to check the inverse filtering operation. If I would like to check the inverse filtering operation from the virtual image, I can even generate the motion blurred image. I do have the code for generating motion blurred image, right? So it is called motion blurred image. With this, we can conclude the last chapter of your image processing. And my suggestion is try to go through and the concepts once and try to implement using your MATLAB. So here, so on the other day, I said all the things can be implemented in the MATLAB. So here, so for a B section, people have shown operations on the image. How do you add images, subtract images, complement, contrast stretching, all the things I have explained them. Image operations and the basis functions, Walsh transform, right? And all the things, parallel transformation. So all the things. Simple example, if I show here, inverse filtering, I would like to show the output of the inverse filtering. And before that, I should know what is the what you call degradation the image due to the motion, right? And all things you can try in the MATLAB. And if you are interested, I'm going to share all the slides and even all the programs here. You please try in the MATLAB. Why? Because it is a practical oriented subject. By going to the theory, you cannot understand much better. I mean, you cannot understand complete subject. You'll complete that is you need to try, you need to implement by taking real-time images. And here I have taken my son's image here and I have tried here, right? Let me try here. A second. So if the size is a big size, it is taken my son's image. Okay, I'll share all the programs even. I'm going to share all the sites.